Hello everyone. In this lecture, we will talk about some properties of matrix. We will first talk about rank of a matrix, then we will talk about determinants and how can we calculate them. Finally, we will talk about eigenvalue problems and single value decomposition. So let's get started with the first definition we have is rank of a matrix. So let's see what is a rank of a matrix. So the rank of a matrix is maximum number of linearly independent row vectors of A. Okay, so this is the definition of a rank of a matrix. So the next definition I want to make is what is uniqueness and infinite solutions. So uniqueness, what do we mean by that? And infinite solutions to our linear system. So by this, let's say we have a linear system of equations with n unknowns. So let's consider we have a linear system of equations with n unknowns. Okay. So we can show it with a coefficient matrix A we had before. So A is A11 to A1n, AM1 to AMN. This we call it coefficient matrix. And we can also define the augmented matrix of that, and we show it typically with this tilde, where we have A11 up to A1n, and then we also have the B1 up to BM, and this would be AM1 up to AMN. Okay, so this is called the augmented matrix. Okay, so these are our linear system equations. So now we define uniqueness as it has only this system of linear system of equations has one solution if and only if the rank of A, which we showed with R, and augmented A equals to n. So the number of equations and unknowns. So if the rank of A equals to n, which means we have it equals to the number of unknowns, then we will have a unique solution. Basically, if number of unknowns and equations are equal. On the other hand, we can have infinitely many solutions, infinitely many solutions if rank of matrix A is smaller than n, meaning we have less equations, less independent, linearly independent equations than the number of unknowns, then we can have infinitely many solutions. So this is how we define uniqueness and infinite solutions. Okay. Now, let's talk about a famous type of linear systems, and that is homogeneous linear systems. So let's see how we define this. So a homogeneous linear system is a system where you're solving AX equals to 0, where A is again an M by N matrix, and this system, this homogeneous system, has non-trivial solutions meaning anything other than 0, right? X equals to 0 is a trivial solution of this system if rank of R of A is smaller than n. Okay, so it has a non-trivial solutions if this rank is smaller than n. Okay, can have many solutions, but at least it had to in order to have any solution, we have to, the rank of the matrix should be smaller than n. Okay, so these solutions plus x equals to 0, this is a trivial solution of this system, form a vector space of dimension n minus r. And we typically call this vector space solution space, or this is very common, null space of A. Okay, so if you hear this, what is null space of A, we mean the solutions to this system AX equals to 0. And we can show that rank of A plus nullity A, or the dimensions of the null space of A, is gonna be n equals to n. Okay, so rank of A plus nullity A equals to n. This is a general statement for homogeneous linear systems. Okay, so this was some introduction about these homogeneous linear systems. Now let's talk about another important topic, and that is Determinants. So what are determinants? When we talk about determinants, it's a very important topic. And how do we define them? So determinants. So let's first define it. A determinant of order n is a scalar associated with an n by n matrix A. Okay? So it's scalar associated with that, and then how we calculate it, it has some definitions, but I think I assume most of you know how to do it. So I'm just doing it for 3 by 3 matrix as an example. So this brings you just refreshes your minds from your undergraduate studies. So just let's calculate it for an example. So I have a matrix and I want to calculate its determinant. So determinant of A for this matrix that I have is like this. It's a 3 by 3 matrix, and the matrix I have is 1, 3, 0, 2, 6, 4, minus 1, 0, 2. Okay, so this is my matrix, and I want to calculate the determinant. I typically show it with like this. And so the way I'm going to do is, first, you will take 1 here, you multiply it by the determinant of these smaller sets, okay? And then you do it for the second component 3, and you sum it up, and then you will get the matrix. So let me just do it. So first, it's going to be 1 times the determinant of 6, 4, 0, 2, plus, now I do it for the second component, and for this one, I have 3, and then I have 2 minus 1, 4. So for the second component, I do it with, it's going to be, the sign is going to be negative because it's the second component. So let me just write it down. Minus 3, 2, 4, minus 1, 2. The determinant of this smaller 2 by 2 matrix, plus the last one. So the last one is, again, I use 0, and then I calculate the determinant of this, okay? So I have 0 times determinant of the smaller matrix, 2 by 2 matrix, 2, 6, minus 1, 0. Okay? So now I calculate the determinant of 2 by 2 matrix, and I think most of you should know that it's basically this component multiplied by this minus this component multiplied by this, okay? So let me just do it for the first one. Is going to be 1 times 12 minus 0 minus 3, 2 by 2 again, plus 1 by 4, plus 0. times 0 plus 6. And if you calculate this, what do we get? We get minus 12. So this would be the determinant of this 3 by 3 matrix. Okay, so when we talk about determinant, we mean this, and then you can actually generalize it for other matrices as well. Okay, so let's see what are some important properties of this determinant. Okay, so one important property is that inverse of an n by n matrix A, we show it with A minus. So the inverse of the matrix is defined as follows. We show it with A minus, and we define it such that A times A minus gives us identity matrix, or equals to A minus times A, and equals to the identity matrix. So the inverse of a matrix is that when you multiply it by that matrix, we get the identity matrix. Okay, so this is the definition of the inverse matrix. Okay, now the inverse matrix A minus 1 exists if and only if rank of A is n, and if determinant of A is not 0. Okay, I'm not going to prove it, but this is a theorem that you can prove, that this only exists if the determinant of the A is not 0. If the determinant is 0, we cannot actually define this and have this inverse matrix. Okay, so this is about some preliminary definitions about matrix operations. Now I want to start a very important topic, and that is eigenvalue problems. So let's see what are eigenvalue problems. It's a very, very common and very important topic in linear algebra, and we will have, it has a lot of implications. So let's see what is eigenvalue problems and what do we mean by that. So eigenvalue problems. Okay. So let's A go to a JK, a given non-zero n by n matrix. Okay, so let's assume we have this matrix A that is non-zero and is n by n. Okay, then we consider this operation where AX equals to lambda x. Okay, so here lambda is an unknown scalar and x is an unknown vector. So here we call these lambdas actually as eigenvalues. So I define eigenvalue of A is value of lambda for a solution of x non-zero x. So if you have a solution, a vector where x is not zero, then we call that lambda as the eigenvalue of matrix A. Okay, what is eigen? Let me just give you a brief overview. So eigen is a German word which means characteristics. Characteristic. So these values are basically the characteristic values of this matrix. Okay. Now, what is eigenvector? Eigenvector is basically the corresponding solutions of x not equal to 0. So all the solutions of x are going to be our eigenvectors. Okay? What do we call by spectrum of A? What do we mean by that? Spectrum of A is basically set of all eigenvalues of A. So when we talk about spectrum of matrix A, we mean a set of all eigenvalues of A. Okay? So this is our definition of eigenvalue problem. Now let's solve one example of that. So we see how can we actually find the eigenvalues of a matrix system. So let's solve an example here. So example. So the example wants us to determine the E value. So sometimes I just show it with eigenvalue like this and E vectors for simplicity of this matrix. A equals to 2 by 2 matrix minus 5, 2, 2, minus 2. Okay, so let's determine this eigenvalue and eigenvectors of this matrix. Okay, so this is our example. So let's start. So I want to solve this. So the answer is as follows. So first I want to define that AX. So AX, want to find those vectors. So let me write this down. So we have minus 5, 2, 2 minus 2 times a vector x, which I don't know what it is, x1, x2, equals to lambda x1, x2. So this is very simple definition of my problem that I had. So I want to find these lambdas and the associated and corresponding x1 and x2 to this lambda, okay? So let's continue. So this is a simple two equations, right? These are just two linear equations. So let me just write them down according to the equations, and let's see what we get. So we have minus 5 minus lambda times x1 plus 2x2 equals to zero. So I bring this lambda to the left hand side, and then I write this. The second equation that I have is 2x1 minus plus minus 2 minus lambda x2 equals to 0. Okay, so I just bring those lambda equations to the left, so I get these equations. Or simply, I can, if I want to show it in matrix form, this is basically A minus lambda I x equals to 0, right? So I just bring this to the left hand side, I get to this equation. So this is a homogeneous system, linear system, it only has solution if it has a solution the determinant of it is not 0, right? This is what we talked about. If you have a linear system, let's get back here. If this system has only a solution if the inverse exists and only if the determinant is not 0, okay? So this has solution if only this condition is satisfied. So what I need to do, I need to calculate its determinant and make sure it is not 0. So let's calculate the determinant of A minus lambda I. So if we calculate that, so this matrix we had is minus 5 minus lambda 2 minus 2 minus lambda. So I can just rewrite those equations that I had in terms of this matrix, or I can just write it based on the original matrix I had and then have this lambda vector there. So what is the determinant of this? It's a simple 2 by 2 matrix. So the determinant is going to be simply minus 5 minus lambda times minus 2 minus lambda minus 4. And if you calculate it, what you get is as follows. So we will get lambda squared plus 7 lambda plus 6 is going to be 0. Okay, so if this gets to 0, then lambda 1 would be minus 1 and lambda 2 would be minus 6. It's a simple quadratic formula. You can calculate it and you will get to these solutions. And now these will constitute my eigenvalue. So these would be my eigenvalues for this 2 by 2 system. Now let's see what are my eigenvectors. So I can calculate now eigenvectors. So for eigenvectors, I said first I do it based on each of them separately. So first do it lambda 1 equals to minus 1. So if I do this here, what I will get is this system of equations that I have. So let me write this down again based on that. So what I will get is minus 5 minus lambda x1. So this will give me minus 4, right? So I have minus 4 x1 plus 2x2 equals to 0. The second equation would be 2x1 plus minus 2 plus 1, which will give me minus 1. So it's going to be minus x2 equals to 0. So I get to this two equation, two unknown system. And now the first equation gives me x2 equals to 2x1, right? The second equation also gives me the same thing. So this means I have infinite solutions here. I can have a lot of solutions. So if we choose x1 equals to 1, then x2 will be 2. So I can just say my eigenvector, one eigenvector is 1 and 2 for lambda 1 equals to minus 1. Okay? So this is one eigenvector. And similarly, you can find it for lambda 2. And you will find the second eigenvector the representative for that is 2 and minus 1. So one eigenvector that can satisfy for second eigenvalue that I had is minus 6 would be this 2 and minus 1. Okay, so this is how typically we find eigenvalues and eigenvectors in a problem, in our problems, okay? So this was a general approach. You can extend it to more complex matrix, like if you have a 3 by 3 or something like that. This is the general approach, that you first calculate determinant of A minus lambda I, you find the eigenvalue simply, and then you find some eigenvectors for those eigenvalues. Okay. Now I want to talk about a theorem about these eigenvalues. Okay, and generalize it. So this is a theorem that I'm not going to prove it, but you can use it in the course. So the theorem is as follows. So the theorem, the eigenvalues of matrix of a n by n matrix, so let me just say n by n matrix A are the roots of determinant of A minus lambda I equals to 0. And for E vectors, for each lambda, we solve A minus lambda I times V, a vector V, equals to 0 to find E vectors. Okay, so this is a general theorem that you can use if you want to find the eigenvalues of matrix. You just calculate this determinant of A minus lambda I, and then for the eigenvectors you solve this equation. And now I want to make another definition before we go to single value decomposition. That's another important topic we have in this course. So the next definition I want to make is also an important definition, is about orthogonality or orthogonal matrix. So what do we mean by that? So let me just put it here. Matrix. So orthogonal matrix is a matrix where its transpose equals to its inverse. Okay, so this is the definition of an orthogonal matrix. Okay. So what does this mean? This means that if I multiply the transpose of the matrix by itself, I will basically get A minus 1 times A, the inverse of the matrix, times itself, which will give me the identity matrix. Okay, so this is a definition of a orthogonal matrix. And this means that if you multiply its transpose by the matrix, you will get back the identity matrix. Okay, so now we have a theorem here that I'm going to prove it. And the theorem states that the determinant of an orthogonal matrix has the value of plus or minus 1. Okay, let's prove this. So proof. So let's see what is a determinant. So these are some properties of determinants that we can use. I'm just going to write it down here. So we can write that the determinant of matrix A times B equals to, this is some identities you can prove, I'm not going to prove it, equals to determinant of A times determinant of B. And another property that I'm going to use is that the determinant of the transpose of A equals to the determinant of the matrix itself. Okay, so with these two in mind, I want to prove this theorem that I said. So I will start with this determinant A square. So I want to find what is the determinant of this A matrix, which is a orthogonal matrix. So I will first start with determinant A squared to see whether I can get an interesting relation for that or not. So what is determinant of A? It is determinant of A times determinant of A. So instead of the second determinant of A, I will write the determinant of A transpose, because it's equal to determinant of A. So it's equal to determinant of A transpose. And using the first property that I wrote here, I can write this as determinant of A times B. If this is A and AT, if we just assume B is AT, I can write it as determinant of A times AT. And what is A times AT, or transpose? Because this is a orthogonal matrix, so A times AT should be based on the definition we made here, and you can see it here. Based on this definition, this should be I, or identity matrix, right? And what is this? This is what I made this. This is determinant of A. So we can write this, or another way, you can just write this as AT times AT equals to A minus 1, and you will get the same thing. But we made that there. This is an orthogonal matrix. And so this equals to determinant of identity matrix. And what is the determinant of identity matrix? Is 1. So this shows me that the determinant A square equals to 1. So the values of the determinant of A should be plus and minus 1. So this actually proves my point. Okay? So this is a theorem that we use here for this type of orthogonal matrix and orthogonal matrices. Okay, so this was a brief overview of all these simple and overall preliminary definitions of matrix operations. So in the next session, I'm going to do work on single value and define singular value decomposition. What is a singular value decomposition? Then we will solve one example of that, and then we will talk about the principal component analysis and how this singular value decomposition can help us to find the principal components in any data sets that we have. Thank you.